Hello, so in this video we will talk about some more definitions about graphs and how we can apply those definitions to solve different problems. So we are talking about paths and connectivity. Okay, so a path is a sequence of edges from one vertex to another. So for example, if we have this is my A, B and C, so my path is A, B and C. Or you can say if this is your E1, this is your E2, your path is E1, E2. Okay. Now this and this are equivalent if the graph is simple. If the graph is not simple, then this is the definition. Then you have to use edges. If the graph is simple, then you can use interchangeably edges or vertices. Okay. So simple path is if no edges repeated. If it has no repeated edge, then it's a simple path. Circuit if the length of the path is positive and the starting vertex is the same as the ending vertex. So for example, if I add another edge here and if I say a E3 here, this is my E3, then this becomes a circuit. Sometimes they are also called cycles, okay, for obvious reasons. Okay, and for undirected graph, a graph is said to be connected if there is a path between any two distinct vertices of that graph. Okay, so for example, this is connected because we can reach, there's a path from A to B, there's a path from B to C, there's a path from A to C. Okay, connected component of a graph. So for example, if we have a graph, then we want to find a proper subgraph of a graph that is not a proper subgraph of any other connected subgraph of G. Okay, so for example, this is essentially, this means that we have, if we have a graph, what is the maximal subgraph of that graph which is connected. Okay, but that has to be a proper subgraph. So proper subgraph is the same concept as proper subset. So it has to be smaller than the actual graph, but it has to be connected. Okay, that is called the connected component. And max, if we find all the connected components of a graph, then the maximum of that will be the connected component. Okay, so by definition, we want to find a subgraph of G that is connected and there's no other subgraph of G that is a superset of that connected subgraph. Okay, that is the connected component. Okay, similarly, we can define connectivity in digraphs. So since we have directions there, then we have to define connectivity differently. So we say if it is if we can reach, if there's a path existing between any two given vertices, different vertices, then it is strongly connected. But if the path does not exist, but if we remove the arrows and then the path exists between those two vertices and all two vertices in the underlying undirected graph, then it is called weakly connected. Okay, so it's obvious that if a graph is strongly connected, it is automatically weakly connected, but the other way around is not necessarily true. Okay, then strongly connected component of the graph is similarly defined for directed graph, that maximal strongly connected proper subgraphs. Okay, now let's apply this whole story here. So is this graph strongly connected or not? Okay, now note that if I take for example A and D, which are farthest apart, so can I reach from A to D, A, B, C and D? Can I reach back? I can reach, can I reach back from D to A? I can go here and then, and this should be this way. I can go here and then I can go only one way and then I cannot go back. So this means this is not strongly connected. Is this weakly connected? So if we remove the arrows, imagine that these arrows are not there. So I can go this way, and this way. And I can go this way, this way, this way. And for example, B to D, I can go this, I can go. So by inspection, you can check that this, and this. We can check that from any vertex, we can go to any other vertex. So it is actually weakly connected. What are the strongly connected components? So this is again done by inspections here. So here we can say that if we say is one vertex of that component. So A, B will be there because from A we can go to B and B we can go to A. Okay, but then can we add C? Sorry, can we add E? We can go to from A to E through B, but we cannot go back from E to A through B. Similarly, C, we can go one way, but we cannot go the other way. But F can be added. From F, so this means this is one connected component, one A, B, and F. So this component here can be any any pair is reachable from itself, okay, from the other vertex, okay. So then the other three are C, D, and E. Now, first of all, let's see whether they are connected or not. So from C, we can go to E. From from E, we can go to C. From C, we can go to D. From D, we can go to C through E. So this means this is also strongly connected components. Sometimes it's also called strong component. Okay. So strongly connected is also known as strong component. Okay. So this is one strong component of this graph, and this is one strong component of this graph. So other thing we will talk about is that paths and circuits can also be used to check whether whether two graphs are form an isomorphism or not. Okay. So what we say is that a circuit of length greater than 2 can be used in isomorphic invariant. For example, if we have this graph and this graph, we can see that this graph has 4 circuits of length 6, which is V2, V6, V7, V2, V6, V7, V5, V4, V3, V2. Okay, and then V2, V6, V5, V7, V8, V1, V2, and similarly V6, V2, V1, V3, V4, V5, V6, and then V6, V1, V3, V1, V8, V7, V6. 4 circuits of length 6, but here we have only 2 circuits of length 6, U1, U2, U3, U4, U7, U8, and U1. And the other one is U1, U3, U4, U5, U6, U8, and U1. So these are only 2 circuits. So this means they are not isomorphic. Okay. But in this video, I also want to share with you a Matlab code for checking whether two graphs are isomorphic or not. Okay. Now you can see that this is a painstaking process because you have to inspect so hard to check whether all the circuits are present or not. Okay. So let's go to check how does Matlab do that. So in Matlab, what we do is our G1 is our first graph. So this is the adjacency matrix of G1. So just as a reminder, what is an adjacency matrix? We have what are the connections of U1 or V1, and this is the second row. So we are only considering the directed part of this. So we assume in Matlab we can assume that they are directed. Okay, and then what we do is we write G2 the same way, and then we use this command sparse of G1 and sparse of G2. This is done so that this graph isomorphism function can be used. So this one, what will it do? It will convert it to a format in which we can write this expression here. So now what is this G1 plus G1? This apostrophe is for transpose. So for what is G1 plus G1 transpose? Remember what we did was we only considered directed edges. So in order to make it undirected, we have to add this matrix to its transpose. And similarly G2 plus G2 transpose. And this is my answers F and M. So now if I run it and check the value of F, it is 0, and M, it is an empty set. Okay, so going back to, so in Matlab what happens is our answer F, if this is 0, this means they are not isomorphic. If it is 1, they are isomorphic. If F is 0, then M is always an empty set because there is no isomorphism present. But if F is 1, then there is an isomorphism. So for example, if I get 1, 3, 2, then this means that this 1 is corresponding to 3, this 3 is corresponding to 2, and this 2 is corresponding to 3. So if it is isomorphic, Not only does it tell you that this is isomorphic, it also gives you a possible isomorphism. Okay, so if it says 1 3 2, then 3 is connected, 3 is corresponding to 2, and 2 is corresponding to 3, and 1 is corresponding to itself. Okay, so this is a short example of some definitions about paths and connectivity, and some small example of how to check whether a directed graph is strongly connected or weakly connected, and how to find the strongly connected components, and then followed by some how can we use paths to determine whether we can check two graphs are isomorphic or not. Okay, followed by some small example how can we use Matlab software to check whether two graphs are isomorphic. Okay, so this is it about this graphs, its paths and connectivity. Hope it was easy to understand, and thanks for watching. Hope you liked the video.